we've got Roger Lenard up next, and he's retired Air Force, over 2,000 hours of single-seat flight time, and was the PM of Project Timberwind, which our previous speaker very kindly left off of that list so that there won't be any duplication, right?
Well, that was good, wasn't it?
Yes, absolutely.
So I want to talk to you about two things. I'm going to talk about the advanced LEU, PBR, and LEU space power systems. So just going through quickly, I was asked by UNM to put together a senior design project because ANS came through and said, you got a good academic program, but your senior design projects are stale. You probably need some new thinking. So I came over there and, oh, yeah, that's right. You have to pardon me. I'm supposed to walk around. I'm not supposed to stand in one spot, you know. This is called Brownian motion. Anyway, so I selected two projects. One was an advanced PBR and TR that used LEU fuels, addressing some issues that we discovered through testing, by the way, in the SNTP program, and then to develop a low alpha space nuclear power system using a well-understood existing reactor concept, which is, by the way, I think the Achilles heel. Everybody comes in and says this is going to be the best power system in the world, but we don't have a reactor, and that'll require 70 years to build, and you know everybody loses interest after a while. So this is a particle bed reactor. I just want to concentrate on the issues. We had observed some hot cracking, primarily because of this lower feature. That was, if you have a packed bed, regardless of how well you try, the particles are going to migrate through thermal cycling, and they're going to settle in the bed. As a consequence, you will end up with a lot of particles at the bottom, and when you heat them up, they'll expand thermally and crack the fuel element. Look, we did a lot of fuel particle testing. We demonstrated you could get really hot particles. But if you can't contain them, then you don't really have a concept that's of any utility. We actually built real fuel elements. We actually built a real particle bed reactor in 18 months from the time the program started. You can do things fast. You can do them well. You just have to do them, because if you don't do them, nothing's going to happen. And then the other thing was some of the ceramic fuel might have melted. Let me tell you a little story. Jim Powell's a great guy, okay? And he said, we can get these fuel particles up to 3,000 kelvins gas temperature. And I said, well, Jim, most of the fuels melt before then. How are we going to do that? And he sort of said, what's behind you makes no difference. You know, I mean, so the point is that part of what I wanted to address here is, how do you get really high gas temperatures without melting the fuel? And the answer is, you melt the fuel, okay? So this was some of the requirements. Here's the deal. Utilize materials to allow for uranium fuel to operate in the liquid regime. Mike talked to you about something that, by the way, I didn't realize there was anything called a liquid fuel NTR. So I invented this thing that did centrifugal containment, exactly like the picture he showed you while I was running the SNTP program. So I wasn't entirely crazy anyway. So what I did, I thought about the problems we had for some time. So I used prior designs as the basis for a 1 gigawatt reactor. We reduced this because we didn't need to have that much power, because I had originally sized it assuming that LEU fuel was going to increase the size of the reactor. Counterintuitively, it did not. I put fuels in a hexagonal close pack with 2 millimeter fuel particles. The fuel particles were made of single crystal tungsten. Why did I make them of single crystal tungsten? Because the people at Glenn Research Center found that single crystal tungsten, well, number one, tungsten does not alloy with uranium. It's one of the few things that doesn't. liquid uranium is about a universal solvent, okay? Meaning that I don't care what you put next to it, it's going to dissolve it, all right? So liquid uranium has a bunch of nasty, nasty features when you're trying to design it for a real system. The second thing is tungsten doesn't alloy, or it doesn't alloy, and single crystal tungsten, it was discovered, would actually contain molten uranium. Did I do something wrong?
No, I was just saying if you wanted to migrate around a bit, there's a handheld mic sitting on.
Oh, well, that's okay. I think I can stick my feet to the floor for a few minutes. Okay. So what I did is I said, what about the problem with the bed migration? So I said, well, look, why don't we try this? Let's go ahead and make these tungsten particles, make them about 2 millimeters in diameter, and then make some ceramic trays that you can put a single layer of these particles in it, and then put it into an induction furnace and sinter the contact points. So now you had a semi-rigid bed instead of a disaggregated bunch of particles. You needed 2 sets, well, you needed a lot more than that if you were going to actually have a tapered flow channel. But you would have 2 types so that they would stack on top of each other. That had a kind of positive aspect. The system would be controlled through moderation and reflection and absorption. By the way, one of the things that happens if you're a good program manager is you don't do anything, okay? The reality is, for those of you who want to be program managers, let me tell you what a program manager does. A program manager solves all the problems that people executing the program can't do, okay? You say, well, what's that? Turns out it's quite a bit. Most of it is battling the bureaucracy into submission, okay? One of the heights of my 10 years as program manager was BWXT. I will never forgive you guys for this, came up to me and said, we need $3 billion worth of clause indemnification for this thing because our company doesn't want to do it otherwise. So how in the world to do that? Well, I discovered that you actually can go to the Secretary of Defense and ask for $3 billion of clause indemnification. That's the path. The issue is actually getting to sign the letter, okay? The secret is you have to have your own little sub-government within the government. And there are a lot of those within the Pentagon. And needless to say, I got it. I breathed a sigh of relief. BWXT says, you actually did it. I think they were hoping that, you know, they could get out of it. So at any rate, so we did an initial core calculation. We found out, so what I did is I had all these fuel particles full of uranium fuel. It turns out there was too much fuel. So they reduced the size of the reactor. They reduced the moderation, and what happened is some actually kind of neat things. This is a cross section. Everybody's talked about that. We came up with a third design, then came up with a fourth design, and what we did was we changed the moderator from plastic at the time, which needed a lot of cooling, to graphite. Well, that's cool because graphite doesn't soften the spectrum so much, so we had a much more uniform absorption of the neutrons through the depth of the bed. And some people would say, well, gee, isn't that going to cause a problem with heat transfer? Yeah, it could, except at the temperatures we're operating, you're starting to dissociate hydrogen. You know what happens to the heat capacity of hydrogen as you start to dissociate? It goes off the charts, okay? And so this is what we ended up with. We ended up with something that had so much worth. We ended up using regular normal tungsten rather than 184 enriched tungsten. And we had to poison it up a little, so we put a little radium in it to ensure that it was not only subcritical, but it it alleviated a lot of the ductile to brittle transition temperature problems. Now, one of the things I'm going to tell you about materials. We are used to normal materials like that chair sort of sitting still, and at room temperature they do. When you're operating at 33 or 3400 Kelvin, you may not see it, but there's a whole lot of motion going on, okay? And one of the motions is that I don't care what material you got, Arrhenius still reigns supreme, okay? And you are going to get diffusion primarily of the lighter fission products through the tungsten shell. Now, there are those of you who believe that we should contain the fission products. I sort of look at fission products as cancers, okay? And you want to get rid of them. And why do you want to do that? Well, supposing you had a nuclear reactor that you ran for an hour, and you have all these fission products inside, what do you have to do? You need to do decay heat removal. Well, typically that means that the hydrogen coming out of the nozzle is a lower ISP than the hydrogen that you have coming out when it is operating in an optimal sense. If you get rid of the fission products, you get rid of most of your decay heat removal problem. So I'm a big fan of just waving the fission products goodbye. And the hotter, the better. So if you aren't bored by this time, you never will be. So this was the finalized core concept. By the way, when I was the program manager of SNTP, we were trying to make this thing compact, and we were trying to figure out how to control it. So I said, look, get rid of the control drums. I've just invented this thing called the peekaboo shutter that will allow us to do control inside the reactor. And I remember them coming up to me and they said, you're crazy, you know, this will never work. And I said, well, why don't you try it? We tried it in the peekaboo reactor, the peekaboo shutter system, in the critical experiment, and it worked great. So don't let anybody tell you you can't do it. So these are the reactivity control, moderation. I already told you about that. The average neutron energy is 0.4 MeV, which is pretty hot actually for a reactor. But you have so much uranium, you're in good shape. And then we did some thermal hydraulics and all this stuff. Now, one of the nice things about the difference between a hexagonal close packed bed, which you get by stacking these various centered elements, is that you don't have correlations for heat transfer. Spherical packed bed, hexagonal close packed heat correlations are well known, and they're analytical. And by the way, there's a big, huge argument. How many of you have met Ergen or Achenbach? Do you know who these guys are? They're really smart guys that developed correlations for packed beds. And there was this like furious argument within the team about which one was right. Turns out it really didn't make any difference because they only were effective in unstable flow at about 1 megawatt per liter, and we weren't planning to spend more than a microsecond or two there anyway. So this is what we ended up with. Temperature in at 33 K, temperature out at 3300. Those are some inlet and outlet pressures, which are not really of very much importance. But the thing that I wanted to go over, this is just all sorts of stuff. I said we wanted a design point of about 1,000. We didn't do that. This is theoretical, of course. We actually got to almost 1,100 seconds, specific impulse, at a thrust-to-weight ratio of about 8. If you have 1,100 seconds to specific impulse at a thrust-to-weight ratio of 8, it's a better mousetrap, okay? Anyway, I don't want to go over a whole lot of these things. I want to talk real quick, like, if you don't throw me off the stage, about an LEU surface power system. Because I'm going to ask, I'm not a very smart person. You know, I want to tell you something. You know these little paper things that go over the toilet seat? Okay? It wasn't until I was 40 years old to figure out how that thing worked, okay? So I can't be very smart. At any rate, so what I want to tell you here is the hardest thing to get over the hump in a space nuclear power system is the reactor. I can tell you this. I don't care how good your system is. If you go to somebody who's going to invest money, whether it is a government decision maker or a commercial investor, if you have to design a brand new reactor and get it licensed and do all these things, you're going to run right smack dab into a empty wallet, which is worse than a brick wall, by the way, all right? So I said, what can I do with a trigger reactor? How many of you know what a trigger reactor is? Okay, are they well known? Nod your head. Yes, they're well known. Are they ubiquitous? You bet, they're all over the world. Are LEU ones ubiquitous? You bet. So let's start with something that is so well known that nobody can argue about its safety, nobody can argue about its operability, and nobody can argue much about its cost for development, because they're all over the place. So these were the design requirements. We had a trigger type reactor. The difference is trigger reactors have big fat fuel elements. However, there is one trigger reactor, the Romanian trigger reactor, which has 5/8 of an inch diameter fuel pins, okay? And it's demonstrated a 64 megawatt days per kilogram of uranium. Really high burnup, okay, like 50%. Then we had a closed Brayton cycle with a bottoming, in this case, supercritical CO2 cycle, with a carbon-carbon finned radiator coated with aluminum heat pipes, ammonia heat pipes. Anyway, here's some cycle diagrams that aren't very interesting. Here's core physics that isn't very interesting. Here's some pretty pictures that only tell us that you could run for 10 years and still be well below the design burnup of the Romanian trigger reactor. And here's we used a 75% mole fraction of helium. The radiators were, I actually invented a radiator, and I built it on my own money and tested it, worked, okay. It was a carbon, K1300S carbon fiber, so it had high thermal conductivity. So their cycle analysis said we had a cycle efficiency of 63%, which is pretty good, okay. If you have something like that, that has big terrestrial implications, as well as deployable military implications. But supercritical CO2 has some undesirable characteristics, which are, it doesn't like to be above 310 kelvins or so for the low end temperature. So what, I told you I was going to give you an assignment if anybody was interested. I've discovered a different fuel than supercritical CO2, supercritical isobutane. Now, why is that interesting? It may be interesting because not only does it radiate at a higher temperature than CO2, but if the cycle diagrams or the Moliere diagrams are right, it looks like you don't have much waste heat, which means that your cycle efficiency could be even higher than 60%. So I'm looking for anyone who thinks they're an expert in supercritical cycles. If you are, please come talk to me. And that's what this last thing is, okay? What we found is that the system-specific mass was 8.5 kilograms per kilowatt. What does that mean? We're sort of in between the 10 kilograms per kilowatt and the 6 kilograms per kilowatt that Franklin Chang Diaz was talking about, which means something really interesting for electric propulsion. It's not the best you can get. I know quite a bit about nuclear electric power systems and nuclear propulsion. And pulling out all the stops, I think I can get to 1 at 20 megawatts. But that's really hard. That's like 2,000 kelvins. This thing runs at 1,250 kelvins. We actually know how to build things at that temperature. So that's all I've got, all right? If you want any more, you'll have to hire someone else. Any questions? Yes. Well, the smart place to test it is in space, of course, okay? However, Mike asked me to come up with a concept for, well, as a matter of fact, look, Marshall's been doing how do you test these things. And they always design their effluent treatment system to capture fission products, okay? But the real question is, if you do a lot of fuel element tests in an existing reactor, which you can capture the fuel elements because there's only one fuel element test. My question is, you know, reactors are just physics, okay? Why not build a rocket and go fly it, you know? I mean, you know, this ain't beanbag. Go take a risk or two. You know, we did that in the Apollo program. So, yes, there are ways that you can capture the effluents where you release the fission products, okay? You have to deal with the waste stream, but you can capture most of them, all right? So I think we can do that. Next. Absolutely, absolutely. That's why you do smart radiators. You can do dumb radiators, but you have to do smart ones if you're gonna cross the threshold of 10.